Video about analyzing your data, which is the part of multivariates data analyze, and this is also the video 6. I call it the part 6 about data analysis, and in this video we'll finish this chapter. We'll start outlier detection. Univariate methods examine all matrix variables to identify unique or extreme observation for small sample. 80 or fewer observation outlier typically are defined as case with standard score of 2.5 or greater. For small sample, 80 or fewer observation outlier. For large sample size, increase the threshold values of the standard score up to 4. If the standard score are not used, identify case falling outside the range of 2.5 versus 4 standard deviation depending on the sample size. Biovariates method focused your use of specified variable relationships such as the independent versus dependent variables. Use scatter plot with confidence interval as a specified alpha level. Multivariate methods best studies for examination. A complete variates such as the independent variables in regression of the variable in the factor analysis. Threshold level for the D2 measure should be conservative, 0.005 or 0.001, resulting in the value of 2.5 small sample versus 3 or 4 in a large sample. Many times they can be accommodated in the analysis in manner in which they do not seriously distort the analysis. An illustrative example of analyzing outliers. As an example of outlier detection, the observation of an BAT dataset are examined for outlier. The variable considered in the analysis are the metric variables x6 through x19 with the context of our examination being a range of analysis where x19 is the dependent variable and x6 through the x18 are the independent variables. The outlier analysis will include univariates and multivariates diagnosis. When candidate for outlier this designation are found, they are examined and the decision on retention or deletion is made. Outlier detection. The first step is examination of all the variable from unique perspective. Biovariate method will then the employee to examine the relationship between the dependent variable x19 and each of the independent variables. From each of these scatter plot observations that fall outside the typical distribution can be identified and their impact on that relationship occurs. Finally, a multivariate assessment will be made on all of independent variable collectively. Comparison of observation across the three method will be provide the bias for the deletion retention decision. Univariate detection. The first step is to examine the observation on each of the variables individually. Table 10 contains the observation with standardized variable values excluding plus 2.5 on each of the variable x6 and x19. From this univariate perspective, only observations 7, 22 and 90 exceeded the threshold on more than single variable. Moreover, none of these observations had value so extreme as to affect any of the overall measurement of the variable, such as the mean of the standard deviation, We should not add the dependent variable had one outlying observation 22 which may affect the bivariate scatter plot because the independent variable appear in the scatter plot. The three observations will be noted to see whether they appear in the subsequent bivariate and multivariate assessment. Bivariate detection. For a bivariate perspective, 13 scatter plots are formed for each of the independent variables x6 through x18 with the dependent variable x19 and ellipse representing the 95% confidence interval of the bivariate's normal distribution is the superimposed on the scatter plot. Figure 5 contains example of two such scatter plot involve x6 and x7 as we can see in the scatter plot for x6 with the x19 the two outlier fall just outside the ellipse and do not have the most extreme values on either variable. The result is the contrast to the scatter plot of x7 with x19 where observation 22 is markedly different from the other observation and shows the highest values on the box x7 and x19. The second part of the table can contain a complication of the observation filling outside the ellipse for each variable because it is 95% confidence interval. We would expect some observation normally to fall outside the ellipse. Only for observation 2, 22, 24 and 90 fall outside the ellipse more than 2 times. Observation 22 falls outside in one of the 13 scatter plot mostly because it is the outlier on the dependent variable of the remaining the three observation. Only observation 90 was noted in the univariate detection. Multivariate detection. The final diagnostic method is to assess the multivariate outlier with the Mahalanobis t-square measure. See table 10. This evaluates the position of the observation compared with the center of the observation seen as the variable in the cases of the metric independent. Scatter Selected scatter plot the bivariate detection of the outlier, X product quality and the X square the e-commerce activity with the X19 customer satisfaction. So this is X19 that is the customer satisfaction and this is the product qualities of e-commerce. Variables were used the calculation of the d square df values. Df is equal to 13 allow for the identification of the outlier through the approximate test of the statistical significance because the sample has only 100 observation. A threshold values of 2.5 will be used rather than the value of 3.5 or 4.0 used in the large sample. With this threshold, two observations 98 and 36 are identified as significantly different. It is interesting that these observations were not seen in the earlier univariates and the bivariates analysis but appear only in the multivariate test. These results indicate that are not unique on any single variable but instead of unique in combination, retention or deletion of the outliers. As a result of these diagnostic tests, no observation demonstrated the characteristic of the outlier that should be eliminated. Each variable has some observation that are extreme and they should be considered if that variable is used in analyzing. No observation are extreme on a sufficient number of the variable to the consider representative the population. In all instances, the observation design as outlier even with the multivariates test seems similar though on the remaining observation to the retained multivariates analysis. However, the researcher should always examine the result of the specified multivariates technique to identify observation that may become outlier in the particular application. Testing the assumption of multivariates analysis. The final step in the examining the data involved testing the assumption underlying the statistical basis. The multivariates analysis, the earlier step of the missing data analysis and outlier deletion attempt to clean the data to the format most suitable for the multivariates analysis. Testing the data for compliances with the statistical assumptions underlining the multivariates technique now deal with the foundation upon which technique makes statistical interface and results. Some techniques are less affected by violating the certain assumption, which is the termed rebootness, but in all cases meeting some of the assumption will be critical to a successful analysis. Thus, it is necessary to understand the role played by the each assumption for every multivariate technique. The need to test the statistical assumptions is increased in multivariate applications because of the two characteristics of multivariate analysis. First, the complexity of the relationship, knowing the typical use of the large number of variables, mark the potential distortions and bias more potent when the assumptions are particularly when the violation compounded to become even more determinant than if the considered separately. Second, the complexity of the analysis and result may mark the indicator of the assumptions violations apparent in the similar univariate analysis. In almost all instances, the multivariate procedure will eliminate the multivariate model and the procedure result when the assumptions are severally violated. Though the researcher must be aware to the assumptions and violation and the implication they may have been estimation process or the interpretation of the result. Seeing the individual variable versus the variate. Multivariate analysis required that the assumption underlying the statistical technique be tested twice. First for the separate variable I think the test for the univariate analysis and second for the multivariate model variates which act collectively for the variable in the analysis and the meet the same assumption and individual variable. This chapter focus on the examining of individual variable for meeting the assumptions underlying the multivariate procedure. Discussing in the chapter address the method of use assess the assumptions of underlying univariates and each of multivariates technique. Four important statistical assumptions. The first is normality, and the second is assessing the impact of the violating and the normality assumption. Third is impact due to the shape of the distribution, and fourth is that is impact due to the sample size. First, we talk about the normality. The most fundamental assumption in the multivariate analysis is normality. Multivariate technique and the univariate concept are all based on the foundation fundamental set of assumptions representing the requirement of underlying the statistical theory, although many assumptions of the requirements come into play in one or more of the multivariate techniques. For our them potentially affect every univariate and multivariate statistical technique. If we talk about the normality is the most fundamental assumptions in multivariate analysis is normality, referring to the shape of data distribution for the individual matrix variable and the correspondence of the normal distribution. The benchmark for the statistical method, if the bivariate from the or normalization is sufficiently large, all results statistically test are invalid. Become normally is required to use the F and statistical, both the univariate and the multivariate statistical method discussed in the next are based on the assumptions of the univariate normality with the multivariate method, also the assuming the multivariate normality. Univariate normality for a single variable is easily tested and number of the collective means are possible as shows later. In a sample sense, multivariate normality, the combination of the two or more variables, means that individual variables are normal in a univariate senses and that their combination are also normal. Those if a variable is multivariate normal, it is also univariate normal. However, the reverse is not necessary true. We are more univariate univariate normality will help gain, although thus the situation in which the variable exhibit univariate normality will help the gain, even though not guarantee multivariate normality. Multivariate normality is more difficult to test, but specialized tests are available in the technique most affected by the departure from multivariate normality. In most cases, assessing and achieving the univariate normality for all the variable is sufficiently, and we address multivariate normality only when it is especially critical. Even though large sample size tend to diminish to determine the effect of the normality, the researcher should always assess the normality all the metrics variable include the analysis assessing the impact of violating the normality assumptions. The severity of the normality is based on two dimensions: the shape of the offending distribution and the sample size. As we will see in the following discussion, the researcher must not only judge the extent to which the variable distribution is normal, but also the sample size involved, when might be considered unacceptable. Second, sample size will have the negligible effect of large sample size impact due to the shape of the distribution. How can we describe the distribution if it differs from the normal distribution? The shape of the distribution can be described by two means: kurtosis and skewness refer to the peakness of the flatness of the distribution compared with the normal distribution. Distribution that are the taller of more peak than the normal distribution are termed leptokurtic, where a distribution that the flatter is the term platokurtic, where the kurtosis refer to the height and the distribution. Skewness is used to describe the balance of the distribution, that is the unbalanced and shifted to an side, right or left, or it is center and the symmetric with about the same shape on both sides. If the distribution is unbalanced, it is skewed. A positive skewness denoted a distribution shifted to left, whereas a negative skewness reflect a shift to the right. Knowing how to describe the distribution is the following by the issue of how to determine the extent of amount of which is different on these characteristics. Both skewness and kurtosis have empirical measurement that are available in all statistical programs. In most programs, the skewness and kurtosis of normal distribution are given value of the zero. The value above or below zero denote departure from the normality. For example, negative kurtosis value indicate a platokurtic distribution, where the positive value denote the leptokurtic, and the distribution likewise. Positive skewness value indicate the distribution shifted to the left, and the negative value denoted the right way shift. To judge the r, they are enough to worry about the quotient for these values. The following discussion of the statistical test shows how to kurtosis and the skewness value can be transformed to the reflect of the statistical significance of the differences are provided guideline as to their survey. Let's talk about the impact due to the sample size. Even though it is important to understand how the distribution depart from normality in term of shape and whatever these value are large enough warrant attention, the researcher must also consider the effect of sample size. Sample size has the effect of the increasing statistical power by reducing the sample error. It results in a similar effect here in the large sample size, reduce the determining effect of the normality in small sample of 50 or fewer observation, and especially if the sample size is less than 30 or so significant and from the normality can have the substantial impact on the result. For sample size of 200 or more, however, these same effect may be negligible. Moreover, when group comparison are made, such as an ANOVA, the differencing sample size between the group, if large enough, can even cancel out of the detrimental effects. Those in most instances, as the sample size of the male much large, the researcher can be less concerned about the normal variables except as they might lead to outlier assumption violations that do have an impact in our way. For example, see in the following discussion of the homoscedasticity. Let's talk about the graphical analysis or normality. The simple diagnosis to normality is a visual check of the histogram that compare the observed data values with the distribution approximating the normal distribution. Although appealing because of its simplicity, the method is problematic for smaller sample where the construction of the histogram, that is the number of the categories of the width of the categories, can distort the visual portrait to such an extent that analyze is useless. A more reliable approach is the normal probability plot, which compare the cumulative distribution and actual data values with the cumulative distribution of the normal distribution. The normal distribution from the strength of the diagnosing line and the plotted data values are compared with the diagnosal. If the distribution is normal, the line representing the actual data distribution closely following the diagonal. Figure 6 shows the several departure from the normality and their representation of the normal probability in a term of the kurtosis and skewness. The first departure from the normal distribution is termed to the kurtosis are easily seen in the following probability plot. When the line fall below the diagonal, the distribution is a flatter than the accepted. When it goes above the diagonal, the distribution is more peaked. The normal curve, the former, for example, in the normal probability plot, a peak distribution we see distinct S-shaped curve. Initially, the distribution is the flatter and the plot line fall below the diagonal. Then the peak part of the distribution moved to the line above the diagonal, and eventually the line shifted to below the diagonal again in the distribution flattened. A non-peaked distribution has the opposite pattern. Figure skewness is also easily seen, most often representing by a sample either above or below the diagonal. A negative skewness is indicated by and below the diagonal. Above the diagonal represent a positive skewness distribution and cancel source for interpreting the normal probability plot, showing that the various pattern of the interpretation is diurnal and wood. These specified pattern not only identify normality but also tell us the form of the original distribution and the appropriate remedy of apply. Statistical test of normality. In addition to examining the normal probability plot, one can also use statistical tests to assess normality. A sample test is a rule of thumb based on the skewness and kurtosis, a value available as a part of the basic descriptive statistical for the values computed all the statistical program. The statistical value z from the skewness value of the calculating as z is equal to skewness underscore 6 by n. These are the examining your data. The chapter here is a normal probability where the curve is rising, the univariate distribution when the curve is in the beginning of the rising, and then it's at the point of certain point of time and then it started decreasing. This is the normal probability plot. This is the univariate distribution, normal distribution. This is a normal probability plot and univariate distribution. This is a non-peak distribution. This is a non-normal distribution. Informal distribution. This is a peak distribution. Normal probability plot the correlation univariate distribution, where n is the sample size, a is the z value, and calculating the kurtosis using the following formula. To specify statistical normality, all the statistical program, two most common and Sparrow-Wilks and the modification of the Kolmogorov-Shimrov test, each of the calculating the level of the differences and the normal distribution. The researcher should always remember that test significant and the less useful in a small sample, fewer than 30, and the quite sensitive in a large sample exceeding the 1000 observation. Those the researcher should be always be both graphical plot in any statistical test and the degree of departure from the normality. Remedy for normality.